40 years from now, I focused on secure software development and product security in various roles, including managing and building up a P-cert, which to this topic I will come later in this webinar as well. And since 2 years, I'm partner of Siemens Product Cert and mostly engaged in handling security vulnerabilities in Siemens products.
Yeah, thank you, Stevie. So just to give you a little bit of more background about Claroty research, so our research team has been very active in the last few years. We've been participating in different competitions, including DEF CON, ICS-CTF. We got Black Badge for winning first place. We participated in S4 competitions, CTFs, and also in Point to Own Miami in 2020. We have hundreds of CVEs or vulnerabilities that we discovered. And today we're going to discuss one of the recent vulnerabilities that we discovered. But before that, I'll let Stevie introduce Siemens P-cert.
Yeah, the Siemens Product Cert, or short P-cert, is a P-cert, a product security incident response team, amongst other areas. And in that part, we manage and handle vulnerability reports from all sorts of security researchers across the world, are engaged with them, with various CERT organizations internationally, as well as, of course, internally throughout the whole Siemens, whenever product vulnerabilities are detected or are to be handled with. We engage with our teams, with the product security officers, with the product teams, as well as with communications, legal, and all sort of other entities internally. And at the end of this chain, always there is a vulnerability disclosure that we publish in form of so-called Siemens security advisories, which provide the information about a vulnerability, what Siemens, as well as the corresponding mitigations and remediation for that vulnerability.
Yes, thank you, Stevie. So let's go over the agenda real quick. First of all, we would like to share with you our story of how we discovered the vulnerability in Siemens PLCs, and then we'll go over on the story of the narrative of how we discovered it, what we did in order to exploit it, and how we worked with the Siemens P-cert and the Siemens organization. How we work together in order to both disclose it, fix it, and prepare mitigations for this vulnerability. So it's kind of a coordinated disclosure success story that we want to share from both sides of the attackers or the security side of it, how we're researching vulnerabilities, and from the protector side, the Siemens, the vendor that is trying to protect its users and make their product as much as secure as they can. So with that, let's start. First of all, we would like to discuss what are PLCs and what are the findings that we discovered. So first of all, we all know PLCs are complex. Basically, in essence, they're machines that run logic in loops, and the goal of PLCs is to orchestrate or to control processes. So it can be manufacturing processes, it can be water and utilities processes, it can be oil and gas related processes. But the main goal of the PLC is to run logic written by the engineers, and this logic is being running and orchestrating sensors and actuators in order to make a process operational. So when we're thinking about PLCs, when we're talking about security in PLCs, we need to consider that the main goal of attackers is to hide code, is to execute and hide code on the PLCs, and they would like to be as evasive as they can. So they don't want their code to be detected, obviously, because then security security professionals could extract this code, analyze it, and maybe discover who's behind the attack. So therefore, PLCs have a couple of mitigations and protections. One of them is memory protection. So the code, the logic that is running on the PLC is sandboxed, which means that the logic that the engineer is writing cannot do whatever they want. It is very limited in what the code can do, and we'll talk about it in a bit more. We also want to emphasize that previous attacks required physical access to the PLCs, or they required the engineering workstations in order to attack and access the PLCs. But the vulnerability that we discovered, which is marked as CVE-2020-15782, is kind of different vulnerability. This vulnerability allows remote attacker, which is in the same network as the PLC, so we need network access. And this vulnerability actually exploits memory protection security on the PLC. So it's a memory protection bypass vulnerability that allows attackers to bypass the Siemens PLC sandbox. And what it means actually is if attackers are exploiting this vulnerability, they can escape the sandbox, so they can actually escape the limits of the PLC, of what the code, the logic can do, and it means that the exploit can write to wherever the attacker wants on the memory. And we'll talk about the implication of this in a bit. The affected PLCs are Siemens SIMATIC S7 1200 and Siemens SIMATIC S7 1500. And if attackers are exploiting these vulnerabilities, they may run code in a protected area of the memory. So it's kind of operating system only areas. And we were able to show that if attacker is exploiting this vulnerability, they can read and write from and to anywhere in the memory, which means that they can also, in a later stage, can execute code. And we'll discuss it in a bit. Let's talk about previous attacks when we're talking about attacking Siemens PLCs. So we had three major attacks that we thought worth mentioning. So we had Stuxnet, the infamous malware. We had the Rogue 7 attack, which was presented in Blackhead a few years ago. And we had Abassi and Chknovsky attack that we're going to discuss right now. So first we had the Stuxnet, the most infamous PLC attack ever. I think everybody are familiar with Stuxnet. It's a malicious computer worm first uncovered in 2010. And the main goal of this malware was to target nuclear plants in Iran to delay their nuclear bomb readiness. So this malware attacked PLCs that controlled centrifuges, and it did it in a very unique way. The malware patched project files of Step 7, of Siemens Step 7, and when the project files were downloaded to the PLCs, the Stuxnet malware was installed in the PLCs, and if the engineer tried to read the code to do an upload, what Stuxnet also did on the engineering station part of the platform was to intercept all the communication between the engineering station or the HMI to the PLC, and it actually replaced on the HMI or the engineering station replaced the code that was reading from the PLC, and that's how it was able to evade any detection. So Stuxnet was an attack against SIMATIC S7 300 and 400, and it's important to notice that this is just an example to attack against Siemens PLCs, and it's completely unrelated to our research. Next, we had Rogue 7, so it was an attack demonstrated by research group against S7 1500, and in this case the researchers actually were able to understand all the crypto mechanisms of how engineering stations, a Siemens engineering station, the TIA portal, is communicating to Siemens PLCs, and they were able to masquerade a TIA portal, so they were able to kind of create their own specific code to connect to the PLC, and by that they were able to decouple the logic that is going to be run on the PLC and the text code that the engineer is writing and reading. What it means actually is the PLC was running malicious code that the attackers, or in this case the researchers, decided that they want to download to the PLC, but the PLC also held a text or the code in a plain text form, so that when the engineer read the code from the PLC, it actually read the textual form of the code, and so this is how the researchers were able to be undetected and stay evasive. And again, let me remind you that the main goal of attackers when we're talking about PLCs is to run code, to execute code on PLCs, but remain evasive, because we all know that we can do download and upload to the PLC, and it's very easy to detect what's the logic that is currently running on the PLC. But if the code is somehow hidden or evasive, it's very hard to detect what's actually running on the PLC. So we presented so far Stuxnet with intercepting the communication between the HMI and the PLC, and now we're with the ROC7. We just presented how researchers were able to understand the crypto mechanisms in order to decouple the opcodes or the logic that is running on a PLC from the clear text form of the code. Finally, we want to introduce Abbasi and Shacharnowski. They presented an attack, a physical attack against Siemens SIMATIC S7 1200, and what they did is they physically connected to the PLC with a physical wire connection, UART specifically, and they were able to find a couple of vulnerabilities and chain them together in order to execute code, but it required physical access. So it's not so good from an attacker perspective, because usually they don't have a physical connection to the PLC. And now we want to move forward a little bit and discuss what we found. So the vulnerability that we discovered is kind of evolution, the next phase of all of the previous attacks, and we were able to insert code into the PLC remotely, and not only that we were able to insert code, we were able to insert code into the kernel memory areas of the PLC. But before we're diving in, let's go over and do a recap of what a PLC is. So as we said, PLC is like a tiny machine or a tiny computer. It contains a CPU and a memory, and we're able to interact with it and insert code or make it run our own logic. And so the main goal of the PLC is to run this logic in order to monitor processes or read information from sensors or send instructions to actuators. And again, it's all to make sure the process is running and to change physical processes. So maybe to turn on a turbine or to read the temperature from one of the sensors, etc. So our logic, or the engineering logic that is running on the PLC, is contained in the sandbox, because the vendors such as Siemens and other vendors want the PLC and the entire process to be as safe as possible. So it's very important to run the code, the logic in a sandbox that will limit the code that is running to do a very defined actions. So the engineer cannot somehow destroy the PLC by mistake, or attacker will not be able to do harmful stuff if they have ability to download code to the PLC. So the sandbox is limiting the resources and the actions that the engineer's logic can do on the PLC. For example, it can only use a certain API functions, and it cannot write to protected memory areas. So the sandbox is very important. It's very important item in a chain of security protections that vendors have developed and implemented in PLCs. Now, specifically the Siemens S7 PLC is running the Adonis kernel, and depending the specific module, it is running ARM or MIPS processor. And PLCs can run a couple of different programming languages that are related to ICS. So for example, ladder diagram or function block diagram, and a couple of more. And they do that by having an intermediate language, in this case the MC7 or MC7 Plus, which all the different languages, different programming languages, are being translated to, and then the intermediate language is transferred to the PLC, and the PLC is executing, is interpreting and executing the intermediate language. So let's see how it goes. We have a couple of different programming languages that are, this is the logic code that is reading by the engineers, by the users. They are being compiled to MC7 or MC7 Plus bytecode, in this case of Siemens, and this translation is being executed on the PLC by a virtual machine. So when we're saying virtual machine, because they're not real opcodes that the processor can execute, they're kind of intermediate language, and then they're being transferred and executed finally by the processor in the native language of the processor. So we have the programming language, which can be some, for example, ladder diagram. It is being translated to MC7 Plus, which is the intermediate language. This is being interpreted by the virtual machine on the PLC, and finally the processor is executing the native code on the PLC itself. Now, what we did in order to escape the sandbox or being able to write to protected memory areas is that we reversed engineered the MC7 and MC7 Plus bytecode language. So we reversed engineer all the platform that handles the MC7 virtual machine or the intermediate language handling in order to understand all the internal parts of it, and we actually found a bug. We're not going to discuss the technical details of this bug because it may put asset owners at risk, but we can say that we found a bug in one of the opcodes, and we were able to exploit it in order to achieve read and write to protected memory areas. So what we did with that is we used this bypass, we used this sandbox escaping in order to kind of jailbreaking the native S7 1200 and S7 1500 in order to write to anywhere in the memory. So we're able to write arbitrary data, and data can be also code, to protected memory areas. So for example, we were able to write our own code into the operating system memory areas, and so we kind of replaced parts of the operating system itself. So when the operating system executed these parts, we achieved remote code execution. So first, we were able to escape the sandbox in order to write to and from anywhere on the PLC. Then what we did with that is we patched an existing VM opcode, or we patched one of the opcodes of the intermediate language on the PLC. This is a protected memory area, and then we used this to write our own shellcode. This is an ARM or MIPS shellcode to internal operating system memory area. And when the operating system itself used this part of the code in itself, it actually executed our own code. And this is how we achieved remote code execution. And we were able to install with that kernel level program with a functionality that is completely hidden to the operating system. So a small diagram for this is currently being shown on the screen. So we can see here that the logic, the engineering logic, is running in a contained manner. So it's running in the green rectangle. This is a user memory running in a restricted sandbox. By exploiting the vulnerability that we found, we're able to achieve write access to anywhere in the PLC. We used it to write our own shellcode to a protected memory area, and we forced the operating system to execute our own shellcode in the operating system. So this is how we discovered the vulnerability, and we're able to exploit it. And with that, I would like to let Stevie discuss what can be done in order to be protected.
Yeah, thanks a lot, Sharon, for this explanation. So I agree with you, and again, awesome research. So thanks a lot for reporting this and coordinating this issue with us. Most interesting point, of course, now for our customers, for our users of the PLCs is what can you do now with this vulnerability? What's the best way to go forward? First of all, as you can see in our advisory, which is also linked on that slide, is there are fixes available for both models of the PLC. If you update the firmware to these versions, then you're done. Because this closes the door, this shuts down the door of this memory bypass, and you're secured again against this vulnerability. So whoever is able to do this immediately should do this, and we strongly recommend this, of course. Beyond that, I'd like to point out that, of course, we also advise to keep your installations, your environment up to date with latest security updates of the different components in order to stay safe. Updating and patching is an important cornerstone of all security measures in OT environments. Of course, I know that not everybody can patch immediately. There is also complexity around that. So what else can you do? Of course, the most important feature here is to protect the access to the PLCs, which means you apply the password protection. The PLCs provide for different levels, access levels, and you need to ensure that the full access is password protected. Lower level access, like the read access or the HMI only access, which, for example, in the HMI context, only allows you to send the data, the configured data, but not manipulate or change code on the PLC. Through that access, you can't exploit the vulnerability, but the full access must be protected, and this is done by an appropriate password. And that's also an important security control in general. It, for example, also prevents from potential other attacks like the one that Sharon also explained already, the Rogue 7, to prevent people from incorporating different code into the PLCs. What else can you do? If you still think there is more to do, there's also a special feature called the NDIS PW instruction on both PLCs, as well as the S7 1500 provides a similar feature on the display to configure access protection that works, that nobody can access the PLCs and change the programs, even when knowing the password from remote. So it would only work locally. There are some stumbling blocks here. For example, if you program the NDIS PW instruction, you must repeat this instruction after every power off and on, because without that it would be lost during the next power cycle. And for the access protection on the S7 1500, This is only effective in run mode, so whenever somebody changes the PLC to the stop mode, it is no longer effective. Just as a hint for you. But again, it is a considerable additional measure if you want to ensure, for example, if you're not sure about the current passwords, you can't change it, set it to different values, but think you want to limit it to a certain set of a small circle of people, then this could be an option you could also apply. And last but not least, defense in depth. We repeat it in all our security advisories. It really works. It's not a buzzword. There are plenty of measures you can and should do. Of course, consider if a PLC is directly connected to the internet. This is not a cloud service. This is a small device with a high range of capabilities, a complex range, but mentioned for use within a protected OT environment. This starts with physical access protection. In this case, for example, whenever an attacker directly accesses the PLC, of course, there are plenty other opportunities, plenty other attack vectors, like accessing the local Ethernet ports directly via display, exchanging the memory card, and so on. These are all vectors that need to be avoided to reduce the risk. On the network layer, of course, as I said, don't put it on the internet, but also not on the office network or wherever. Apply the appropriate security layers around your OT environment to ensure that the accessibility from a network perspective is limited to those systems and those people who really need that access. And last but not least, this emphasizes again the last two slides, using the built-in security capabilities, in that case especially the access level protection. And while we are on built-in security capabilities, we also added the hint to the new TLS version 1.3 based communication with the PLCs, which was introduced by end of May and released with the latest firmware versions of the PLCs, which provides a standard-based secure communication and includes the authentication of the PLCs based on individual server certificates. It allows you to run all the communication between HMIs, TIA portal, and the PLCs through encrypted standard-based communication, including a forward secrecy, which means that even if at a later point in time you find out the certificate, the private key of the PLC that is used for encrypting the TLS layer, you cannot decrypt the messages that were exchanged. So that's really an additional layer of security, but I also like to note that the use of TLS does not directly resolve this particular vulnerability. It's just a recommendation to apply an additional and significant new built-in security capability in an OT solution. So that's from my point of view, and at the end of the talk I wanted to recap again what Sharon already mentioned in the beginning, the disclosure success story, so how we collaborated in this particular case. Let me first pick how we work in general at Siemens. If you contact product@siemens.com, we have a well-defined vulnerability handling and disclosure process. So whatever reports we get, we analyze them and handle them together internally with the potentially affected product teams, as well as with you as researchers or whoever is reporting this to us. And at the end of the chain, as I said already, there will be a disclosure of these vulnerabilities through Siemens security advisories. And whenever you like, then we do this in a coordinated way, as it exactly happened also in this case. What happened in this case? I like to wrap up that we have a very good collaboration with Claroty. It's really an awesome team, highly skilled experts here. We receive a very high quality input from them. There's an open communication, continuous information exchange with them, which really runs smoothly in order to avoid any misunderstandings, to go forward in sync. So this is really a great honor to work with you and fun as well as the support we receive from Claroty whenever we have questions about this or that detail in a particular vulnerability. This all works quite well, and I would also say there's a mutual trust on that whatever is exchanged, what is significant and what cannot be shared outside really stays in the room between Claroty and the product cert team at Siemens. And last but not least, of course, whenever we propose a disclosure date, then Claroty is happy to deal with that, and so far we always come to a common understanding on what and when we disclose, as it happens in this case as well. So then I'd like to hand over again to Sharon to put his view on that as well.
Yeah, so thank you, Stevie. I agree 100% with everything that you just said. We're enjoying working with you as well. And yeah, I think the Siemens PCert is one of the greatest PCerts around the world. We're working with lots of PCerts, and it's very very high quality PCert that we're working with. Great response time, great information being delivered back and forth. Thank you very much for all the good feedback. From our perspective, as I just said, we're doing lots of coordinated disclosures with many vendors, many cert organizations. I think in the last previous 2 years, we disclosed more than 130 vulnerabilities to all the major ICS vendors, and obviously Siemens is one of them. And it's really great to work with such a mature and responsible PCert. Whenever we're conducting the research and finding a vulnerability, we're kind of immediately preparing a POC and thinking a lot about the story. And the story means how an attacker would abuse and use the vulnerability that we just discovered potentially, and we're preparing a POC that demonstrates that. So if it's a remote code execution, we're trying to be as close to reality as we can, and we're doing all the protections that the vendor and the manuals are suggesting, and we're trying to bypass this. And in this case, it was exactly like this. So we prepared a POC, we prepared a very detailed report, we shared it with the Siemens PCert. They immediately responded that they are working and analyzing our report and are working on our POC. A few days after that, we had a meeting, a call with them, and we discussed the potential mitigations, the potential fixes for the vulnerability, and we really worked closely with the Siemens PCert in order to both understand exactly what the vulnerability means, how an attacker would abuse this, how to fix the vulnerability in terms of code and mitigations, and eventually on the disclosure itself, what is going to be disclosed to the public and what not. And it was a very pleasure to work with Stevie's team. And I think that's it for now. We have a couple of questions that we don't have much time, but we'll try to work on a couple of questions that we just received. So I think the first question we have is, what kind of access would an attacker require to pull off this type of an attack? What would an attack or initial foothold look like? So this attack requires network access, but not only network access, it also requires a password to the PLC. So it requires download permissions to the PLC. So in a theoretical scenario, the attacker would already be inside the OT network or any adjacent network that can be routed to the PLC. So we're talking about layer 4 and above type of communication. And so the attacker would need to communicate with the PLC, and if the PLC is password protected, the attacker will also need to obtain somehow the password, and then the exploitation can occur. Next question is this type of an attack something restricted to nation states or advanced attackers versus script kiddies? So this particular attack and particular vulnerability is highly complex. We did not disclose the technical details. We only discussed the overview in a very high level because this is a very complex and complicated attack. It requires a lot of understanding around how machine code works, how CPU and the virtual machines are working, how intermediate languages are working, and and be very have an intimate knowledge with the Siemens MC7 Plus framework. So we decided, again, together with the Siemens PCert, that we will not disclose the technical details. So attackers, advanced attackers, nation-state sponsored attackers will not be able to use this vulnerability and maybe do some harm to asset owners. But this is definitely a very sophisticated attack. I believe only nation states or advanced attackers will be able to pull off this kind of attack.
Yeah. If I may jump in here, I agree with you fully. And the point is really there's also a debate ongoing because we rated this vulnerability with an access complexity as low, as high rather than low. So definitely, as you asked, script kiddies are not the ones who can simply pick some exploit, run it, and are successful. So it's also on the side themselves, because it's a really complex thing. You need to adapt this individually for each and every firmware version. So that's in the gray zone between attack complexity low and high. So yeah, I agree with that.
Mm-hmm. Yeah, thank you, Steve. I agree with this as well. So another question we have here, I think, Steve, you can take this. Implementation of TLS into PLC communication partially decreases visibility, which might be provided by Claroty tool. Okay, so I'll take this. Your point of view, what is more important? Thank you. So there are ways to handle this. You're correct. And actually very right that when we want to have visibility, it's kind of if you want to encrypt your entire network with TLS, so it's not easy to obtain visibility. And our tool, the CDD of Claroty, is obviously relying on reading the network feed. And if it's protected and encrypted, it makes our life kind of harder. There are ways to we have some methods to handle this. I can give you a couple of examples. So, for example, we can, by using Siemens TLS mechanism, it's certificate based, and the user can prepare their own certificates. So if we're being given these certificates, so we can work with our users and the customers in order to obtain visibility. And there are also other ways to obtain visibility if we're delaying the encryption after we're seeing the traffic. So if it's something of your interest, we can discuss this later in more depth. Other questions? Hey, how many S500 and S1200 in operation are currently password protected according to estimation?
Yeah, that's... Do you want to answer? I can make some statements.
Go ahead.
So honestly, I don't know. I don't have the numbers, but what I can tell from the feedback we received after our advisory disclosure is that a lot of customers came back to us asking, I have this and that protection on. Is this sufficient to prevent? And I said, yes, you have the right password access level already configured. So I have from now 100% ratio, but of course that's by far not significant. I can hardly assume that a lot of deployments are not password protected, and as well there will be some maybe integrated systems where no password is applied to the PLC. So it depends then on the individual deployment whether this is an issue or not.
Mm-hmm. Yeah, I tend to agree. So my feedback from some of our customers, at least, I did not speak with all of them, obviously, but I do know that the majority of them are using password protection on their PLCs. And again, we're talking about the new series of Siemens PLCs, this S7 500 and 1200. Contain lots of security protection mechanisms, and obviously we're recommending to use at least some of them, if not all of them.
Yeah, but yeah, honestly, both you, Sharon, and I are in the teams who usually communicate with customers who have a sense of security already. So yeah. I expected it, and all these unknown customers who also won't join this webinar, I think because they don't know about, they might not have a password protection on. So it's about awareness on the on applying the minimum security capabilities and security controls in deployments worldwide.
Yeah, I agree. So you need at least a bit of sense of security in order to know at least what to look for. To read manuals and to activate the security options whenever applicable. Mm-hmm.
Yeah. There's one more question. This PLC is used in vast amount of industries, sold in the open market and now widely connected to the internet. How does Siemens follow up customers except for their website service? Is this a part of the warranty service of new control systems? Well, warranty in that sense, what we're talking about is more or less the software, the software support. So how long is a software that applies to a certain product being supported with fixes? And fixes include vulnerability fixes. And as you might know, in this